Hello everyone, welcome to this class on written orders of reaction and compartment models in drug uh, disposition. So first and foremost, we're going to talk about a few content outline, written orders of reaction. We look at nonlinear pharmacokinetics, compartment models. We see the single compartment model, the double or two-compartment model, and three-compartment models. By way of introduction, let's look at rates and orders of reaction, since it forms the basis for most of what we'll be discussing. Now, why do we study pharmacokinetics or clinical pharmacokinetics? Basically because pharmacokinetics is the study of the rate at which drugs reactions occur. It's a mathematical way to help us simplify what happens during absorption. That's after administering a drug, either intravascular or extravascular. So what happens to the drug? How is it absorbed? How is it distributed through the body? How does metabolism happen? And then excretion, when does excretion occur, right? So it's truly in helping provide information to give us an insight into the mechanism of changes involved, which you will shortly see, and allows us to predict the changes that will occur after the administration of the drug. In terms of rates and orders of reaction, the the rate of reaction can be described as the velocity with which a reaction or a process occurs. And this is important because in all the phases of a drug's transmutation, that a drug's change in the body, you will need to understand how fast this change is occurring in order to predict the next step or how the drug is reacting in the body. Now, this whole process is also moderated by a constant, which is known as the rate constant, K. The manner in which this concentration of drug influences the rate of reaction of process is called the order of reaction. For example, zero order means the concentration of the drug has no influence on the rate of progression of the reaction or the rate of the process of the drug or of the change in the drug concentration. It doesn't depend on the concentration of the drug administered. So a zero order reaction simply means that the concentration of the drug does not affect uh, the the rate of the process's progression. So, for example, if you see this example where drug A is um, is undergoing a process to become drug B, or for example, drug A, the concentration of drug A in a particular part of the body is changing, or equilibrating with another part of the body, right? The rate of this reaction is moderated by a constant K. Now, the rate of forward reaction can be described by the change in concentration of this drug A over time, right? Or if we're looking at a backward reaction, the change in concentration of B with time. In this case, let's stick with looking at how drug A changes to drug B. Now, in a zero order reaction, what it means is that the change in concentration of drug A over time can be described by the rate constant times the concentration of the drug A that was first introduced into the body. Now, the concentration of that drug A in a zero order reaction will be raised to power zero. Of course, we know that any expression raised to the power of zero becomes one, right? So minus k times one will give us k. So we can describe that the rate of change of the concentration of drug A in a zero order reaction is minus k, that's rate constant. So this is not influenced by the concentration of the product at all. Now, this is different in a first order reaction. For example, you know that in a first order reaction, the concentration term will be raised to the power of 1, right? So the change in concentration divided, the change in concentration over time will be equal to minus K times concentration of the drug at the first instance. Integrating this equation, we'll get the natural log of C at a time t, or the concentration of drug in the plasma be equal to the natural log of the initial dose that was administered minus KT. That's on integration. Now you will notice that this looks very much like a straight line graph. So if you plot it on a straight line graph, what you would get, if you plot this on a straight line graph, you will get, something like this. Let's say that's the y-axis, and then that's the x-axis. So what you will get will be something like this. Okay. And then, of course, we know that the slope is a negative k. Okay. Now, if you can also change, so that this will be the slope, of course, the negative k, right? Since the equation for a straight line graph is y equal to b plus mx. So our m, which is the slope, will be minus k in this instance, because we're plotting concentration against time, right? Now, when if we change this to the log form to treat the concentration terms, you find that the log of concentration at time t will be equal to the log of the initial concentration of that drug, which is here, right? This will be, of course, the maximum dose that was administered to the body, which will be the initial dose administered minus, and then you have your slope minus k over 2.303, and then times time. Okay, so this is kt over 2.303. Okay, now if we solve for example, we look at what time it would take for this initial concentration to decay to half of its value, right? Which would now change this t to t half, and we solve for that equation. We'll get t half is equal to 0.693 over k, which is still the rate constant. Now, what this means is that half-life is independent of the concentration of the reactants. Okay, so in this equation, you can see that both 0.693 and k cannot change, right, for a particular reactant in the body. So therefore, half-life of all first order reactions are, constant. So 0.693 over k. Since both values are constant, half-life is independent of initial concentration in a first order reaction. Please note that first order reactions please note that first order reactions, most of our reactions are first order reactions in what's it called? In this when we're talking about what's it called? When we're talking about compartment models. Okay, I'm trying to close this. Okay, Now on, let's quickly talk about second order reactions. They're not very important in compartmental models, but it's important to understand it as well. If, for example, a rate of reaction or a rate of a process is described as a second order reaction, the stoichiometric properties invert the concentration consideration. Okay, so the change in concentration of the first drug of that drug over time will be equal to the rate of that process time multiplied by the concentration of the drug raised to power 2. On integrating this, you get 1 over um, the concentration of that drug at time t will be equal to Kt plus 1 over the initial concentration of the drug at time equal to 0. Now, because this equation has a form similar to a straight line plot, right? If you do a plot of the inverse of the concentration, right, as a function of time, you get a straight line similar to what we had in the last, in the first order reaction. But note that in this case, the slope of the reaction is equal to 2k, not k in this case, okay? So the slope of the reaction, which you will get, m that you will get from this reaction will be 2k. Sorry, this is supposed to be 2k, okay? So whatever you get from um, your equation, remember to divide m by 2 to get your k. Now let's quickly look at pharmacokinetic models since they Now, on to discussing pharmacokinetic models. The results of various studies in drug absorption, distribution, and elimination have led us to the concept that the body can be treated as if, there were boundaries separating the system into parts. It's assumed that a drug is transferred from one part, called a compartment, to another in conformity with first order kinetics. Remember we mentioned in the earlier session that drug movements or drug reactions from one compartment in the body to the other, or its transmutation or change within the body is guided by the first order kinetics. Now, in reality, of course, we know that the body is made of lots of thousands of parts, of course, but then it's just for the basis of explanation or for the basis of modeling, predicting how drugs are changed or transformed in the body. It's in that, in a bit to do that, that we try to visualize the body in terms of compartments. Okay. For example, a compartment can be considered as a group of tissues with similar blood flow and affinity for a drug. Okay. It has, of course, no real world anatomical section or physiological reality. It's just a mathematical description of parts of the body that have similar blood flow and affinity for a drug. Now, it's also important to note that the volume described by a model is not the volume of fluid as such, but it's just the volume of fluid that would have contained the amount of the drug at the concentration found in blood. Okay, we're going to see why that is so shortly. Okay, so like I've said, models are mathematical descriptions of the biological system, and the aim of that is to help us make sense of what happens to a dose of drug when we administer it, also to understand why toxicity happens at some doses but not at others, for some types of medicines and not others. Okay, so essentially, we're going to be studying that. Of course, pharmacokinetic models provide concise means of expressing mathematically or quantitatively the time course of drugs throughout the body and helps us compute meaningful pharmacokinetic parameters. Of course, you know that there's no drug that's approved for use without appropriate pharmacokinetic parameters being defined. Okay, there are about 3 ways you can, do mathematical modeling for the body. There's a compartment model, there's a non-compartment model, and physiological. For this level, we'll be talking about compartmental models, and we'll try to explain why this is useful. Okay, the complexities of the human body and physiology would appear to make it impossible for us to have a simple model to use to describe the body and how it handles a drug. However, the fate of several drugs in the body has been described by either one or two compartment models, although some drugs have been shown to be best described with a three-compartment model. And a popular example is insulin when it is given IV. Okay. A compartment is a unit of as a unit characterized by 2 parameters, namely concentration and apparent volume of distribution. Okay, A stands for the amount or the concentration of the drug, the amount of the drug that's administered into the system. As an example, we could look at let's try to take an example so we can define what we mean by volume of distribution at all. Now, I've mentioned that the apparent volume of distribution is hypothetical, or it's used to describe the volume of distribution that would have contained the amount of that drug at the concentration found in blood at that time. Okay, so volume of distribution is a hypothetical value, and let's prove it by doing this. So let's assume that we have 2 tanks, tank A and tank B. Okay, so we have 2 tanks, that's tank A, and then we have a second tank, tank B. Okay, now both of these tanks are the same size, and so this is tank A, and then this is tank B. Okay, now this is 50 liters and this is 50 liters. Now let's assume that we fill tank A with 50 liters of fluid, while we fill tank B with fill tank B with some fluid, and also charcoal. Okay, now assuming this is what we've done, okay, we realize that the 2 tanks are the same volume. Now we know that this is the same volume, so that's not so much a big challenge. Now what we now do is we introduce 100 milligrams of paracetamol into tank A and introduce 100 milligrams of paracetamol into tank B at the same time. After 5 minutes, we withdraw 5 ml sample from tank A and we withdraw 5 ml sample from tank B. And then we try it and calculate the concentration in that 5 ml sample. Let's assume that for tank A, we get 2 milligrams per liter, giving us a volume of distribution of 50 liters. That's the dose, which is 100, divided by the concentration, which we determined from the sample, will give us 50 liters, right? Now for tank B, the sample we withdrew from this tank yielded 1 milligram per liter. So by the time we did our calculation, we have 100 liters. That's 100 over 1. Of course, that will give us 100 liters, right? Now, the idea is we know that this tank is actually 50 liters. But what the concentration of that fluid that we withdrew from this tank shows us is that the free fluid in this tank is at a concentration of 1 milligram per liter, right? Meaning that this appears to have distributed 100 milligrams of the drug in 100 liters of water, which is of course bigger than the actual volume of tank B. Since most of the drug have been absorbed by the charcoal, do you understand? So this is what happens. So what we usually do is an estimate, and it is usually larger than the physical or the actual volume of the plasma or the body score or other tissue volume at that time. Okay. Just to buttress again, the apparent volume of distribution is not the true volume of fluid in the tank, right? It is termed apparent, just to describe a distributional volume in which there is uneven distribution. Remember that there will definitely be higher concentration on the charcoal than inside the fluid in tank B. Okay, so just to note that this is used for description. Okay, and this is an important application for volume of distribution. We use it to estimate the amount of drug present in the body at any time point by multiplying apparent volume of distribution with the plasma concentration at that time. Okay, very, very key. It's one of the uses for the volume of distribution parameter. Now let's quickly talk about the one-compartment open model. So we can describe the body as one compartment. If you look at the body, that when you introduce a drug, it is immediately or instantaneously distributed all over, the body. If you look at this lower part of your screen, you'll see that the blood and other tissues are in one tank, all of them being perfused equally. This is a hypothetical situation, and it does not apply to all drugs. But for drugs that appear to be immediately and instantaneously distributed, we describe them as appearing to be distributed in one compartment open model. And if you plot a concentration, if you plot the concentration against time on a semi-log gradient paper, you're going to have a straight line graph. Now, there are a couple of assumptions that follow each compartment model, and we're going to delve into that soon. But note that the one compartment model is the simplest model. Okay, it assumes that following drug administration, that's when drug is introduced into the central compartment, right? The drug is immediately and homogeneously distributed throughout all the tissue and body fluids for which the drug has affinity. Once the distribution phase is completed, equilibrium is established between the drug in the blood or central compartment and other peripheral compartments in the body. Hence, the levels of drug in blood are proportional but not necessarily equal to those found in any of the tissues or fluids into which the drug is distributed. The concentration at the site of action of the drug is expected to be in equilibrium with plasma drug concentration as well. It is therefore assumed that a correlation should exist between the pharmacological effects and the blood level of drug, particularly when free drug concentration is measured. Note that blood is the only fluid in the body which is in constant contact with all living cells in the body. Okay, it's also accessible for sampling. It's easily accessible for sampling, and that makes it, um, one of the most used substances to measure drug effects or drug levels in the body. Okay, so note that in this model, this is the central compartment into which the drug is administered, just this block, which looks like a tank, right? So once the drug is administered into the blood, it perfuses all of the body tissues similarly and alike immediately, okay? And then elimination of that drug out of the central compartment also happens and is described by the rate constant, okay? Next, let's talk about the two-compartment open model. It's been found that the assumption made, that we made in that one-compartment model with respect to immediate distribution of drugs, it does not really work. Even when you do bolus administration of a drug, it can be justified. Invariably, this means that the distribution process requires significant time for it to achieve some sort of equilibrium between drug in the blood and drug in other body fluids and tissue. A bolus dose of such a drug would give plasma level curve on a semi-log paper which does not decline linearly as you would expect for a one-compartment model. You remember that on the one-compartment model, our plot was a straight line graph that declined linearly. Okay. Now, for this other graph, for this other plot, you will find a biphasic character in the plot. So it becomes necessary to add another compartment to justify what is happening in the second phase of the plot. Okay. Now, the additional compartment is known as the peripheral or tissue compartment. Now, drug in the blood, right, moves rapidly into highly perfused organs like, hepatic portal system, extracellular fluid, endocrine glands, into the skin, the muscles, the bone marrow, adipose tissue, the brain, the heart, all of those get perfused immediately. So there is rapid, passing of drugs into those structures. But there is another compartment which is signified by that second phase in your semi-log plot that will show adequately that there is, a slower equilibration, that's a slower movement of drugs into the tissue compartment. The tissue compartment is considered as less perfused than other compartments. And of course, it is made up of structures like the bones, the cartilage, the ligaments, teeth, tendons, and our hair. Okay, so if you look at that image on the right hand side, you see that the central compartment, which is one, is where you administer your dose. Once you administer drug into plasma or into blood, which is signified by the central compartment here, it rapidly equilibrates into the central compartment, like we have described earlier on, and begins to move into, and then through the rate constant K1 to 2, begins to move into tissue compartment 2. But note that as molecules are moving into tissue compartment 2, their movement is still disorderly. So some of those molecules will still move back into compartment 1. That is described as rate K2 to 1, rate of reaction or rate of movement of the process of movement of molecules from 2 to 1. Of course, we expect that at the early phase, when the tissue compartment is less concentrated to the central compartment, K1 to 2 will be faster until when the tissue compartment is saturated, and then there will be equilibrium between particles moving back into central compartment and those moving from central compartment to tissue compartment. Also note that all elimination only occurs from the central compartment in all compartment models. Elimination only occurs from the central compartment, right? So, which is described by the rate of elimination, constant K, okay? If we plot a graph, like you can see here, of concentration against time, it will show the first phase, which is phase A, and the second phase, which is phase B. It will show you biphasic plots. This is what I was talking about earlier on, that there is a biphasic plot, right? Now, when you have this biphasic plot, this shows you that beyond what has happened here, there is still another, beyond, we don't have that straight line graph, but that shows you that at this point, you're having equilibration happening, and then at this point, you're having elimination from the central compartment, beginning to determine, the concentration that is left in blood. Now, so this at least adequately shows us that there are two phases in this compartment that we're talking about. Okay. Now, the assumption for this two-compartment model includes: one, drug enters into and leaves the body only through the central compartment. That's one. Number two, rate of elimination K, rate of process K from compartment 1 to 2, and rate of process K from compartment 2 to 1 affect other rate constants. That's very, very key, because it determines how we describe the models mathematically. Now, the next assumption is that at time t equal to 0, concentration in the tissue compartment is 0. That's a very important assumption. It also will show up when we begin our mathematical treatment of this model. Okay, an initial rapid decline here depicts the distribution phase from central compartment through to equilibration with the tissue compartment, and then the second, or the much slower terminal phase, represents the elimination segment of the drug. Okay, and so it's important that you note that the apparent volume of the central compartment is denoted as Vp, which you can see here, while the apparent volume of the tissue compartment is denoted as Vt. You're going to see that shortly. Now, we can describe an equation to say the concentration of the drug administered into this two-compartment model. That's, to describe that the concentration found in plasma at a certain time can be equal to A times e raised to the power minus alpha t plus B times e raised to the power minus beta t. Now, these are the alpha is a rate constant for the distribution phase, this phase, so it's the slope of this phase, while the beta is the rate constant for the elimination phase, which is this part of the graph. Now, A is the intercept on the y-axis for this part of the curve, while B is the intercept on the y-axis for this part, for the B curve. Okay. Now, we also make another term, dP, which is the amount of drug in the plasma. Of course, we know that the concentration of A, this point on the y-axis, can be given by D, which is the dose that was administered, divided by the volume, the apparent volume of plasma multiplied by the rate constant for that determines how molecules are moving from compartment 2 to 1 minus alpha divided by beta minus alpha. Now, this B is also treated in the same way. The dose that was administered at time 0 divided by volume of plasma into the volume of plasma multiplied by K from 2 to 1 minus beta divided by alpha minus beta. Now, these equations can be used to solve if you cannot do direct extrapolation. These equations can be used to get the concentration for the B, which is or the intercept of B, and can be used to calculate the intercept for the A part of the curve as well. Okay. Of course, the alpha can also be gotten from the slope of this phase, and then beta can be gotten from the slope of this phase. Now, let's also talk about half-life. How can you calculate the half-life of a drug that has a two-compartment model? You can determine this in two ways. You can determine by calculation, or you can determine it directly from, the elimination part of the curve. You do not use distribution part because it will overestimate the volume. It will overestimate the half-life. So you use the slower part of the curve, which is the B phase. Okay, so determination can be carried out from the terminal segment of the concentration time graph during which elimination occurs. At that point, alpha already tends to 0, while beta will be more at that point. Okay, so you're not having distribution happening anymore. What you're having happening is elimination, because equilibration is reached here when alpha is equal to beta, but beyond that point, you have alpha will tend to 0, while beta will, be greater than alpha at the elimination phase. Okay. Now, what you have is, if you substitute that alpha tends to 0 at that point, of course, we also assume that the concentration of A during the B phase will be tending to 0. So if you substitute 0 at that point for A, you have this part of the equation becomes 0 plus, that's what you have here. So that part of the equation has become 0. And then what you have is concentration in plasma will be equal to B times E to the power of minus beta T. But this is still a complex equation. So what you want to do is, you want to integrate this equation. You do the natural log, and then you do the logarithm, and then you have log of the concentration of plasma is equal to the log of the concentration of B, or the intercept on the y-axis for the B phase, minus, of course, beta times time divided by 2.303. Like I said, this is the calculation method. Another method is you can plot a graph if you have the values, and then you can extrapolate from the graph and then get the slope for that part of the graph. Okay. What you just do is, sorry, not the slope. What you do is, you take one concentration, and then you look at the time it takes for half of that concentration. For example, if you take 20 milligrams per dl on the y-axis, then what you do is you go next to 10 milligrams per dl and check that point, and then extrapolate to time, and then look at the difference, and that gives you the half-life. Of course, the half-life is constant and will not change throughout this throughout this phase. Okay, so your half-life, either by extrapolation on the graph or by calculation, you get the same thing. Now, haven't talked about the half-life. Let's talk about something very important. I mentioned that the apparent volume of distribution can be used to determine if a dose is toxic. Okay, it can be used to determine how to dose a drug. Okay, in the two-compartment model, we have to deal with more than one volume of distribution. In fact, there are about 5 volumes of distribution. But for the sake of this class, we're going to talk about only 4 of them, and then we'll mention the last one. Okay, one is the apparent volume of plasma. There's the apparent volume of distribution at steady state. There's the apparent volume of tissue. Then there's the apparent volume of distribution calculated by area under the curve. And then there's the last one, which is apparent volume of distribution by extrapolation. Okay, now let's quickly talk about apparent volume of the central compartment, which is volume of plasma. Okay, the volume of the central blood compartment is derived from the assumption that all drugs are introduced, into the body through this compartment. Therefore, we can write the mathematical expression to say apparent volume of plasma is equal to the dose administered divided by concentration of plasma at time 0. Of course, we know that at time 0, T is equal to 0. So we can rewrite that equation, that's this equation, this concentration equation, we can rewrite it by putting T as 0 in both of these equations. We will knock out E raised to power minus alpha T and E raised to power minus beta T, because those expressions become 1. Okay, so once those expressions become 1, the concentration of plasma will become A plus B. Okay, so therefore, substituting Cp in this equation, we now have, therefore, volume of plasma, or apparent volume of plasma, is equal to the dose administered divided by A plus B. Of course, the volume of plasma can be used to derive the Cmax following bolus dose of a drug with multiple compartments and calculated doses. Okay, this is very important. Now, let's quickly look at apparent volume of distribution at steady state. Okay, when equilibrium is reached between the central and tissue compartment, the rate of movement of drug from central compartment to the tissue compartment is equal to the same rate from the tissue compartment back to the central compartment. Remember, I mentioned that at that point, K12 becomes equal to K21, right? Okay. So once that has happened, then we can also, once we say K12 is equal to K21, we can begin to say that the dose in the tissue compartment times the rate of change in the tissue compartment will be equal to the dose in the central compartment or the plasma compartment times the rate of movement of drugs from the central compartment to the tissue compartment. Okay, now, therefore we can rewrite our volume of apparent volume of distribution at steady state to be equal to Vp, that's apparent volume of distribution in plasma, into bracket 1 plus K12 divided by K21. If you notice, it is the true distribution change happening in the body, and it is not affected by drug elimination, because this already happens before elimination begins to take place. So this true distribution does not, it is not affected by drug elimination. Okay. Now, let's talk about apparent volume of distribution in the tissue compartment. The value of the volume of the tissue compartment can be inferred from the fact that, as indicated above, right, in the VDSS equation, right? There's my question again. Wow, this question will be clear, right? That at steady state, that volume of distribution is a sum of all the volumes both in the central and the tissue compartment. That's what's happening at, apparent volume of distribution at steady state. It's a sum of both volume of plasma and volume of tissue. Okay, so from the above equation that we have under VDSS, we can already see that here we already have the volume of plasma plus volume of plasma multiplied by K12 over K21. This term, this second term here, multiplied by VP, is actually the term for the apparent volume of distribution in the tissue. So and just pull out that expression to say apparent volume of distribution in tissue is equal to volume of plasma times the rate of change from plasma to the tissue compartment divided by the rate of change from the tissue compartment back to the plasma. So this expression can give us the apparent volume of distribution for the tissue compartment. Which is the product of the fraction of the distribution rate constant, K12 over K21, times the volume of the central compartment, which is VP. Now, another volume of Now, for the apparent volume of distribution by area under the curve, it's important to note that even though this can describe the one-compartment model, right, we can write this same term for the two-compartment model. Okay, that's we can get the volume of distribution by dividing the dose of the product of the elimination rate constant, which is Ke, times the area under the curve. That's the concentration time plot. Okay, now once we have that, this term, for this term, we can further simplify it, and then we get the volume of distribution by area equal to the total dose administered divided by the rate of that change. That's the slope of the B phase times the area under the curve from 0 to infinity. But we also know that total clearance from the central compartment can be calculated by dose divided by the area under the curve from 0 to infinity. So therefore, if you look at this, you can already see that it's similar, excepting for beta that is there. So it means that we can replace that part of the equation to say volume of distribution by area under the curve can be determined by clearance, total clearance divided by beta. Okay, so this shows us that the volume of distribution by area can be determined in terms of the rate constant for overall elimination and loss of drug from the central compartment. Okay, so therefore, we can write another equation where we say the total clearance is also equal to the clearance from the central compartment, since clearance only happens from central compartment. So the clearance from central compartment can also be described as the rate constant times volume, apparent volume of distribution of plasma or um, the central compartment. Okay, so by substituting that, you now get this term. Okay, when we say volume of distribution by surface area by area under the curve is equal to K, that's the rate constant, times apparent volume of distribution of plasma divided by beta, which is the elimination rate constant. This volume of distribution is commonly quoted and used for those calculations because it is easy to calculate. Once you can calculate the volume of distribution in plasma, you already know, you already know the K, right, in the equation, and then you can extrapolate beta from the graph. So this is usually used in practice for determining those calculations for drugs. Now, I said that there were 5 volume of distributions that we're going to talk about. Now, the extrapolated volume of distribution is a volume generated by dividing the dose of the drug with the intercept obtained on the y-axis on extrapolating the terminal phase of the plasma level curve to the y-axis. Okay, now this is done basically just to get those calculations done. But note that the extrapolated volume of distribution is usually gives us the largest answer. So you get a volume of distribution that is large and does not take into cognizance the distribution phase when the drug is being distributed between the central compartment and the tissue compartment. It is usually larger than when we estimate volume of distribution using area under the curve, and of course that is also larger than when we estimate apparent volume of distribution in the central compartment. Okay, so now why do we study volume of distribution in central compartment area in central compartment models? The significance of understanding the effect of volume of distribution in a two-compartment model can be demonstrated if we consider the administration of a rapidly administered loading dose based on the apparent volume of distribution as Vp plus Vt. The initial plasma concentration, which is Cp, will be much larger than predicted because our initial volume of distribution will only be Vp. However, the consequences of such an inaccurate prediction depends on whether the target organ, that's the organ on which that drug has been introduced into the system, that's where it will work. If, for example, the receptors for that drug are located within the central compartment, then if we underestimate the volume of distribution, we can get toxicity. But if, for example, the target for that drug is located in in the tissue compartment, then except we have a larger volume or a larger concentration equilibrating into the tissue compartment, there will likely be no toxicity. Okay, so this is important. Adjusting the loading dose of a drug based on apparent volume of plasma may be considered necessary for drugs with receptors in the central compartment. This is required when the route of administration is intravenous. In the case of extravascular routes like the oral routes or patches or other routes apart from IV, okay, Ka is usually much lower. That That's the rate of absorption from the lumen of the intestine. Okay, is usually much smaller than the rate at which drugs are moving from the central compartment to the tissue compartment, therefore making the absorption step the rate determining step in such administration. The initial plasma concentration from the loading dose may not give a toxic level because of the effect of the absorption step. For drugs like digoxin, which have their target organs in the tissue compartment, the initial high plasma concentration values are usually inconsequential both for therapeutic and toxic levels. This is because the plasma concentration value before distribution, is complete, um, is proportional. Do not reflect. Do not reflect tissue concentration. But after distribution, let me take it back again. I said the reason why you don't have toxicity because of the high CP values, you don't have therapeutic effect or toxic effect, is because the plasma concentration value before distribution is complete does not reflect tissue concentration. It is only after equilibrium is reached between central compartment and tissue compartment, okay, that you will now be able to say that plasma concentration of digoxin is proportional to tissue concentration of digoxin. For example, a minimum of 6 hours is required for equilibrium to be obtained when digoxin is administered via the oral route. This means that any blood sample taken from a patient in less than 6 hours following oral administration will not give us a plasma concentration that can be used for therapeutic drug monitoring. Okay, very key. Now, still talking about the two-compartment open model, let's talk about the area under the curve. This is obtained, from extrapolation on the curve, and of course, mathematically, the expression is similar for that of the one-compartment model too. It's given by the dose of the drug divided by the product of the volume of the central compartment and the rate constant for drug loss from the central compartment, which you can see in this equation. Okay. Now, also, total clearance is the product of the apparent volume of distribution and the terminal elimination rate. You've seen this in the last when we're doing the estimation for volume of apparent volume of tissue, right? So when we're doing estimation for apparent volume by area under the curve, okay. Now we can now substitute volume of distribution as volume of plasma plus volume of tissue. But we also know that at this point, elimination is only happening, that's clearance is only happening from plasma. So therefore, volume of tissue will not come to play in this case. So this is why you have clearance from plasma is equal to K, which is the elimination constant, times the apparent volume of the central compartment. Now, this is one way to do it by mathematical calculation. Another way to do it is you can just compute it from the AUC plot on the graph. With that, I think we have dealt with the formulas for computing both the AUC and the total clearance for a two-compartment model. Also, you may need to calculate this alpha and beta. Remember, I mentioned that you can easily extrapolate them from the graph. For the alpha, you calculate from the A phase, and the beta, you calculate from the B phase. Basically, you calculate them by extrapolation from the curve or from the plot. Now, this concludes our discussion about a two-compartment model. Just by way of information, there is also a three-compartment model. Like I said, it is most often used to describe the kinetics of insulin when it is administered by IV. Okay. In this model, you can explain by some drugs you cannot adequately explain their concentration time plot using that plot that we saw on that two-compartment model, because after the first phase there's a second curve and then a third inflection of the curve, right, which shows that there is you're not considering two phases at this point, you're looking at a likely three-phase event. Okay, so that means that for the three-compartment model, you're looking at that, but there may be a third group of tissues that may be receiving or equilibrating with plasma, at a much slower pace. Okay, and what we usually call that is we call it deep tissue compartment. So that usually forms the third compartment. So there's the first compartment, which has rapid distribution. Of course, we've seen what examples there are. And there's a second compartment, which we said is much slower than the first compartment. But there's a third compartment, which is much slower. Okay, distribution from central compartment. So therefore, you need to add a third compartment for such drugs. Examples are bone and fat tissue. Okay, these are examples of a third compartment. The deep tissue compartment may also represent highly bound drug in the tissues. So if the drug is highly bound in tissue, then you may be able to describe some tissue area as the third compartment. Okay, the semi-log plot of plasma concentration versus time is not linear but triphasic in this case, and requires a tri-exponential equation to describe the curve. Okay, like I said, this is just for mention, but you can see the equation that describes the concentration plot. Cp is equal to AE to minus alpha T plus B E to minus beta T plus CE raised to the power gamma T. And like I said, it's most typified by administration of insulin by IV. With that, we have come to the end of our discussion on compartment models. Thank you very much for listening. God bless.